Welcome back. In this video, we're going to finish off chapter 16 by looking at bond dissociation energy. We can use bond dissociation energy to estimate the enthalpy change of a reaction by taking the sum of the energy required to break the bonds minus the energy given off when new bonds are formed. We're going to be able to do this after looking at chemical potential energy and reminding ourselves of how energy is stored in chemical bonds. So we've looked at these figures already back in chapter 9 and chapter 6 of the ebook. The figure on the left is looking at how the energy of two hydrogen atoms varies as a function of the separation between those atoms. The figure on the right looks at a simplistic model of the attractions that exist between the electrons and the nuclei, and the repulsions that exist between the nuclei and between the electrons of a two hydrogen atom system. And so what we can glean from these figures is that there is an ideal distance for the atoms to be separated from each other in order to maximize the attraction and minimize the repulsion. All bonds are formed because there is an electrostatic attraction between the electrons of one substance to the protons of another substance. And because those opposites attract each other, they result in a more stable, lower energy system. And therefore, our chemical potential energy is stored in those bonds. And when we break a bond, because we have an attractive system, a favorable system, it requires energy to pull those substances apart from each other. They want to be close to each other because they're attracted to each other. So it requires energy to break a bond. Therefore, the opposite process must also be true. If you form a bond, then energy must be released. Let's apply this now to looking at chemical reactions. So the bond dissociation energy is the energy that's needed to break a bond for a molecule in the gas phase. Looking back at our hydrogen-hydrogen system, let's take a look here. So for a diatomic molecule, such as the hydrogen molecule or the oxygen molecule, the bond dissociation energy is the enthalpy of reaction for that chemical reaction. So we take hydrogen, we split it apart into two hydrogen atoms. The energy required for that reaction to occur is equal to the bond dissociation energy. And the reason for that is because there's only the one bond within the molecule. For polyatomic molecules, however, the bond dissociation energy must be obtained by averaging over many different molecules. So, for example, if we look at the hydrogen-oxygen bond in water, we could dissociate one hydrogen from the hydrogen and oxygen, and that requires a certain amount of energy. Or we could look at the hydroxide molecule itself and separate the oxygen and the hydrogen there. That requires a different amount of energy. So for the oxygen-hydrogen bond, because it occurs in a variety of different scenarios, the tabulated value for the bond dissociation energy is actually an average of different scenarios that exist. In this case, we're looking at the hydrogen-oxygen bond when it's within water or hydroxide, but it could also be as part of an alcohol or as part of a carboxylic acid. So for bond dissociation energy values in this case, they're not exactly accurate for any one particular case. So when you use the bond dissociation energies to calculate the enthalpy of a reaction, it actually is just an estimate. It's not an exact value. So let's summarize here. We've talked about how for chemical reactions, anytime we break a bond, that requires energy. When we form a bond, that releases energy. So if we want to look at the energy of a reaction where we take ethane and react it with chlorine gas to produce 2 molecules of methyl chloride, we can determine how much energy is involved by looking at the bonds that are broken and summing up the energy required to break those bonds and accounting for the energy released for every bond that is formed. So we can look at this in a stepwise process. Again, applying Hess's law. Hess's law allows us to get from point A to point B in any number of paths, and the enthalpy of that reaction is going to be the same regardless of the path. So let's say that we take and we start here. We could first take and break the carbon-carbon bond between the methyl groups. We could then break the chlorine-chlorine bond between the chlorine molecule, and then form new chlorine-carbon bonds. That's going to get us then our 2 molecules of methyl chloride. So how do we calculate this? Well, when we do this type of calculation, it's as if we take the bonds that are the energy of the bonds broken and subtracting the energy of the bonds formed. Typically, when we've looked at these types of calculations before, we said take the enthalpy of the products minus the reactants. But for bond dissociation energy, with the bonds that are broken, these are our reactants, and the bonds formed are our products. And so it appears as though it's the reverse. Now, why is that? And that's again because breaking bonds requires energy, whereas when any bond that is formed, it gives off energy. Therefore, the enthalpy of reaction is really just the sum of all of the steps. And because when we form a bond, it gives off energy, that is going to mean that there's a negative sign for that step. All right, so let's take a look at an example. If we want to determine the heat of reaction for the decomposition of 1 mole of hydrogen peroxide, we can use the bond dissociation energies to do so. So the first thing that we need to do is make sure that our equation is balanced. On the left side of our equation, we have 4 hydrogen atoms. On the right side, we have 4. We have 4 oxygen atoms on the left and 4 oxygen atoms on the right. So we're balanced. Then what you want to do is draw out the molecular structures. You want to draw the Lewis structure so you know what bonds are present. Hydrogen peroxide looks like this. And we have water and oxygen. And I recommend writing out each molecule when you have multiple of them, so that way you can count up the total number of bonds of each type. And so we want to count up the bonds that are broken, and we want to count up the bonds that are formed. So there are probably the simplest way to do this is to count up for each possible bond type. So we have 2 oxygen-oxygen single bonds that are broken and none that are formed. We have, so the net is that we broke 2 oxygen-oxygen single bonds. For oxygen-oxygen double bonds, we don't break any, but we do form 1. And so the net there is that we formed 1 oxygen-oxygen double bond. For the oxygen-hydrogen single bond, we break 4 of those, but we form 4 of them. And so there's no net change. For the hydrogen-hydrogen bonds, there are none that exist to begin with, and there are none that we form. But it's important to verify for each possibility. So what we see here is that we break 2 oxygen-oxygen single bonds, we form 1 oxygen-oxygen double bond, and that there's no net change for the other types of bonds. So we can find the enthalpy of reaction by using the net energy of the bonds broken minus the net energy of the bonds that are formed. So we can take the number of oxygen-oxygen single bonds, which is 2, and subtract the number of oxygen-oxygen double bonds, which is 1. That then is 2 moles times the energy per mole, 146 kilojoules per mole for an oxygen-oxygen single bond, minus 1 mole times 495 kilojoules per mole for the oxygen-oxygen double bond. So in total, that gets us 203 kilojoules given off when 2 moles of hydrogen peroxide decompose. However, the question is asking for the heat of reaction for decomposition of 1 mole, so we need to account for that. So we have 203 kilojoules given off per 2 moles, so that's 102 kilojoules per mole approximately that's given off. If you look up the actual enthalpy of reaction for this decomposition, then the published value is negative 94.6 kilojoules per mole. So this is really close to the value we got using the bond dissociation energies. But notice that it's not exactly the same. And the reason for that is because the bond dissociation energies are computed by taking an average of different chemical structures and the energy required to break those bonds. That's it for this video. Thanks for watching. Have a great day.